In this video, we're going to look at how to use polar coordinates to evaluate certain double integrals. Okay, so in this video, I'm going to assume that you have at least a small working knowledge of polar coordinates. If you don't, I did post a quick video that introduces polar coordinates and looks at a few examples along the lines of things that we're going to need for this section. So I'd recommend that you take a look at that if you haven't already. So in terms of how we would use polar coordinates for double integrals, let's suppose we wanted to evaluate this double integral, the integral over r of e raised to the negative quantity x squared plus y squared dA, where r equals the unit disk, right? Which is in Cartesian coordinates x squared plus y squared less than or equal to 1. So it's the unit circle with the interior filled in. This looks like something that we should be able to apply Fubini's theorem to and use integrated integrals to compute. The problem is when we write down either of the two iterated integrals that we need to compute, they are impossible to solve. We'd need to find an antiderivative of this function in terms of either x or y. And since this function's symmetric in x and y, either of them are going to be similar difficulty, but it turns out that it's just simply impossible to do. There's no way to write down an elementary antiderivative for e to the negative x squared plus y squared in terms of x or y. And so at that point, we cannot compute the integrated integral, and we're stuck. However, there's two things about this problem that screams polar coordinates. The first is that the region that we're integrating over is a disk. It's the circle with the interior included. And we know that circles and circular regions like this are easily represented using polar coordinates. In fact, using polar coordinates, this unit disk is just given by r ranging from 0 to 1. And so this is quite easy to describe. The other key that might make us think polar coordinates is the exponent of our function. In the parentheses there we have x squared plus y squared. And in polar coordinates we know that x squared plus y squared is equal to the polar coordinate r. Right? And so substituting r in for x squared plus y squared makes this integral in a polar form very simple. And we don't have to worry about having a sum of squares as the exponent. And so those two things indicate that polar coordinates might be the right way to approach an integral like this. Right. But before we go and just plug everything in and compute, we do have to look at sort of how we would define an integral, a double integral, using polar coordinates. So to look at this in general, let's suppose we have a function of two variables, but in this case the variables are given by polar coordinates r and theta. It's defined on a nice region R. Right, we've talked before what nice means. So it's on a nice region R. That's also described using polar coordinates. All right, so we need not just the function to be in polar coordinates, we also need the region to be described in that way. Right, so we need both. Okay, so we have this function described in this region. And as a quick reminder, this nice means that the region is bounded on each side by continuous curves in terms of polar coordinates, and that our function is continuous over this region. All right, so given this setup, if we would use, we're not going to go through the derivation, but I'm just going to say using a similar double Riemann sum computation like we did with double integrals. So using this similar Riemann sum computation, we can show that the double integral over the region R of the function f of x, y, dA, and I do mean a function f of x, y here, because we're going to convert it to polar coordinates. So this can be computed using the iterated integrals from theta equals a to theta equals b, and then from r equals g1 of theta to g2 of theta. So we're going to allow r's to be functions of theta, of the function f of r cosine theta, comma r sine theta, multiplied by r dr d theta. So this is our formula for integrating an integral using polar coordinates. The only thing that we have to be really careful of, and the thing that's most easily missed by this calculation, is this multiplying by r of our function. And this is just a byproduct of the conversion. Almost anything that involves computing in polar coordinates will involve multiplying by r when we start doing the things with integrals. And so this is a very standard thing, but something that if you're not comfortable with, you do often miss. Right, so let's take a look at a couple examples where we want to compute double integrals using polar coordinates. So first, let's look at how we would find an area of a region using polar coordinates. So let's say we want to find the area of region R that is inside the circle R equals 3/2 and outside the cardioid r equals 1 minus cosine theta. So whenever I'm solving something with polar coordinates, one of the first things I do is always try to sketch a picture of the region, because that can help immensely with determining where certain values should be. And so in this case, I have two relatively simple curves to graph. So I have this, the circle r equals 3/2. And so that circle is a circle centered at the origin and has a radius of 3/2. And so I'm going to go ahead on my grid, on my axes here, I'm going to go ahead and label 2 units out in either direction. And so the circle r equals 3/2 is just the circle that intersects all of our coordinate axes at plus or minus 3/2. And so it looks something like this. Right? So this is r equals 3/2. We want to go ahead and graph r equals 1 minus cosine theta. For those of you that watched the previous video on polar coordinates, I actually graphed that cardioid in that video. And so it's the cardioid. It'll start at the origin. It comes up, crosses here at 1, crosses here at 2, crosses here at 1, and then comes back to the origin. So it looks something like this. And so we want the region inside the circle, but outside the cardioid. So that would be this region that I'm shading in green now. Okay. All right, so we have this region here. And so when we go to do this, we need to be able to do two things. We need to find the functions that I called G1 and G2 in my iterated integral on the previous slide. That's going to be pretty clear. That's going to be our two functions. We need two functions, r equal in terms of theta, and we have them, r equals 3/2 and r equals 1 minus cosine theta. So those are going to be the two bounds for the integral with respect to r. The thing we really need to work on is what are the bounds for theta. And so we can kind of see here where they should be. One bound is going to be this bound here. And so this would be theta equals a. We're going to start there, and then we're going to rotate all the way around until we hit theta equals b, which will be given right here. And so that's going to be our rotation. So we need to find the angle theta that gives us our two intersection points of our curves. And so the way that we find the intersection point, is to set the curves equal to each other. Right? So we want 1 minus cosine theta to equal 3/2, and we want to find the two values of theta that work. And so if I subtract 1 from both sides, I get negative cosine theta equals 1/2, which means cosine theta is equal to negative 1/2. And now looking at the picture, I know I want theta equaling A to be a negative angle. Right? I want to start at the negative angle and move to the positive angle, theta equals B. And so I know the cosine is going to be negative 1/2 at multiples of pi over 3. And so theta equaling A, we can actually think of that as negative 2 pi over 3. All right? We really know it is 4 pi over 3, but if we want it as a negative angle, that would be negative 2 pi over 3. And similarly with theta equals B, we know we want the angle in the second quadrant and we want it to be positive, so that would be positive 2 pi over 3. So these are our bounds for theta in our polar integral. The last piece of information we need in order to compute this area with a double integral is that we want to compute an area, and so we need to know what function to use. And we looked at this in one of the videos on double integrals, and when we want to compute the area of a region, we want to integrate the function 1 over that region. And so this is going to be the function that we integrate. All right, so with this double integral all set up now, we can just go ahead and compute the integral. Right? So our area A, using the iterated integral we set up a little bit ago, is going to be the integral from negative 2 pi over 3 to positive 2 pi over 3 of the integral from 1 minus cosine theta to 3/2, because we want the area outside the cardioid and inside the circle, of the function 1 times r, that was our kind of our conversion factor, dr d theta. Right? So this is the integral that we need to compute. Right? And integrals involving polar coordinates are typically a little bit unpleasant to compute because of the nature of them, but that's just the way it is, unfortunately. However, we can often use symmetry here. So I have the integral from negative 2 pi over 3 to positive 2 pi over 3. And if we look at this particular picture of the region we want to compute the area of, we could actually, instead of going from negative 2 pi over 3 to 2 pi over 3, we could actually just compute the area from 0 to positive 2 pi over 3 and then double it. So what we're doing is we're going to compute half of the area and then just multiply that by 2. And this will be easier to compute because it'll be easier to evaluate a function, particularly trig function, at 0 than it is at negative 2 pi over 3. Right, so we'll be able to do this. All right, so this is one thing we can often do. We can't always do it, but oftentimes this is possible. Right, so now we have to integrate this function with respect to r. So we have 2 times integral 0 to 2 pi over 3. Right, the antiderivative of r is going to be r squared over 2. And so to simplify this a bit, I'm just going to include the r squared, and I'm going to go back out here and I'm going to erase that 2. The 2 and the 1/2 are going to cancel. And so we're just going to have the integral of this function r squared evaluated from 1 minus cosine theta to 3/2. And all of this d theta. Right, so we have this integral here. So this is just the integral from 0 to 2 pi over 3 of 9/4 minus 1 minus cosine theta quantity squared d theta. And so we can expand this out and get 9/4 minus 1 plus 2 cosine theta minus cosine squared theta. Right, so when we look at this, we see I'll simplify this constant in a bit, but we see we have a constant, we have 2 cosine theta. Both of those terms we can integrate nicely in terms of theta, but cosine squared theta does not nicely integrate as itself. So if we go back to our integration methods that we've learned before, you might remember that in order to compute to find the antiderivative of cosine squared of theta, we need to use the half angle identity, and that is that cosine squared of theta is equal to 1 plus cosine 2 theta over 2. Right? And so we're going to replace cosine squared theta with this quantity. Right? So this is going to be the integral 0 to 2 pi over 3 of 5/4 plus 2 cosine theta minus 1 plus cosine 2 theta over 2, all d theta. Right, we're almost at the point where we can integrate. So I'm going to subtract off the 1/2. So we will end up with 3/4 plus 2 cosine theta minus 1/2 cosine 2 theta. And now now everything in sight is easily anti-differentiable in terms of theta. And so we have our antiderivative 3/4 theta plus 2 sine theta minus 1/4 sine of 2 theta. And we want to evaluate this from 0 to 2 pi over 3. Right, and so we have 3/4 times 2 pi over 3, and that's going to be pi over 2. We're going to have 2 times sine of 2 pi over 3. Well, sine of 2 pi over 3 is square root of 3 over 2. We multiply that by 2, and we're just left with square root of 3. And we have negative 1/4 sine of 2 theta. So sine of 4 pi over 3 is going to be negative square root of 3 over 2. And then multiplying that by negative 1/4, it's going to become a positive square root of 3 over 8. Right? And we're subtracting the form with 0 when 0 is substituted in, and this is actually 0 across the board. Each of those is equal to 0. And so we just have this number here, which I'm going to make no effort to simplify. If you really want to add the square root parts together, you can do that, but don't really care about that right now. This is a perfectly fine number, and so this is the area of that region: pi over 2 plus square root of 3 plus square root of 3 over 8. So we'll end this video with the example that we used to start it. So let's say we wanted to evaluate the function, the double integral of the function e to the negative quantity x squared plus y squared with respect to area, so that double integral, where r is the unit disk, x squared plus y squared less than or equal to 1. Right? So as we said, there is no elementary antiderivative for this particular function in terms of x or y, so the polar coordinates approach is absolutely necessary. Right? And so this integral when we apply the polar coordinate conversion, we want to describe the unit disk. So the unit disk, we want to make a complete rotation. So we want to go from theta equals 0 to theta equals 2 pi. And we want r to range from 0 to 1. Right? So these boundaries here will describe the unit disk precisely without having to do any x squareds plus y squared. So it's very nicely described in terms of polar coordinates. And our function, e to the negative x squared plus y squared, as we see that we know that x squared plus y squared is equal to r squared in terms of polar coordinates. So we've converted the function to polar coordinates by replacing the x squared plus y squared with r squared. And then we have to multiply by r. Right? This is, again, the one thing that's sometimes problematic. But in this case, it actually works out algebraically to be necessary, because if we just had e to the negative r squared, we would not be able to compute an antiderivative. But once we multiply it by r, now we're able to compute an antiderivative for this function. Right? So we can make a quick substitution here. I can let u be negative r squared. And if u is negative r squared, du is negative 2r dr. Okay. And so if I want to, notice I have an r dr I want to replace, so we can think of that as du over negative 2 is going to equal r dr. And so that r dr can be replaced by this quantity here. Now we also have to worry about the endpoints as we go from r to u. So r equals 0. We'll go to u being negative 0 squared, which is 0. So our lower limit of the inside integral will remain 0. But when r is equal to 1, u is going to go to negative 1 squared, which is negative 1. So we do have a limit change on the upper limit of integration. All right, so when we go and make this substitution, we're going to introduce a negative 1/2 constant, which we can pull outside all of the integrals. That's from the du over negative 2 being r du. I have the integral of 0 to 2 pi. I've done nothing with theta. The integral of r has now changed from 0 to negative 1. And then this is of e to the u du d theta. All right, so we've changed the integral of 0 to 1, e to the negative r squared r dr, to negative 1/2, integral 0 to negative 1, e to the u du. This is a standard u substitution from single variable calculus. At this point, this integral is quite easy to compute. So we have negative 1/2, integral 0 to 2 pi. An antiderivative of e to the u is just e to the u, and we're evaluating from 0 to negative 1. So we have negative 1/2, integral 0 to 2 pi of e to the negative 1 minus e to the 0, which is 1. So we have e to the negative 1 minus 1. Notice that that is just a constant. Right? And since that's equal to a constant, when we find an antiderivative of it, we just take that constant times theta. Right? And we want theta to go from 0 to 2 pi. And so we have negative 1/2 times the quantity e to the negative 1 minus 1 times 2 pi minus e to the negative 1 minus 1 times 0. And so, of course, this term is 0, so it disappears entirely. In this case, we have the 2 and the negative 1/2 out front cancel, and so we're left with negative e to the negative 1 minus 1 times pi. Right? Or if you would prefer, you could always write this as 1 minus e to the negative 1 times pi. Right? Either way, either one of these options are fine. But this integral was actually quite easy to compute using polar coordinates, whereas in standard coordinates, it's impossible to compute.